As all of you know that magnetism is a quantum phenomenon. Classically, it doesn't exist. Okay? So, invariably quantum mechanics will be involved. Whether you like it or not, the quantum mechanics will be there. And also another ingredient that is required is the stat mech. Okay? So, both these things will be mostly required to have the basic formalism for magnetism. So today in this lecture I will talk about what is called the direct exchange. Direct Heisenberg exchange to be more precise, because it was the Heisenberg who actually used Heitler and London approximation, used that method to find out what happens when you are dealing with a helium atom or a hydrogen molecule. Okay, so you are dealing with two electron system. In a two-electron system, how do we arrive at the interaction between the two electrons when the electrons have both charge as well as spin? Okay, so that is the basic problem. So first what we will start with, we'll deal with just two electron system. Okay, could be a hydrogen molecule, but we'll treat as a first step. In the first step, we'll just treat them as non-interacting electrons, okay? And so that we can label them. You can say this is electron 1, this is electron 2, and then we can interchange the second electron with the first. So we start with that approximation. So both the electrons see the similar potential fields, okay? And so then we can write the Schrodinger equation. For the two electron system, the Schrodinger equation will be just this, which is actually the two Schrodinger equations and take the sum of them. That's all. So this energy would be simply the energy of the individual electrons, basically. So if I call that EA, one of them EA, the other one EB, then E equal to EA plus AB. Okay, so what will happen now is that the possible wave functions are just the one electron product functions, okay, and those product wave functions would be this. This is now two electron wave function, which is just the product wave function of two electrons. So psi A1 is, let's say, electron 1 in some state A. Similarly, psi B2 is the second electron in the state B, and vice versa when they are interchanged. The eigenvalue total for the two electron system is now E is equal to EA plus EB for both the cases. Whether you take this as the wave function for the total two electron system or this one, both will yield this as the total energy of the two electron system. Now each one of them, this energy is the solution of individual Schrodinger equations, which is, for example, for electron 1, Schrodinger equation is this, and with a eigenvalue EA. Similar thing would be for the electron 2, okay, which will have the energy EB, so that the total energy is just the sum of these two. Okay, this I already told you is that psi B2 is the solution when the electron 2 is in the state B, and the other thing, like if electron 2 is in the state A, electron 1 in state B, and so on. Okay. Now we know that we cannot distinguish between electrons; they are indistinguishable. Okay. So now, then what should happen? Okay, since the electrons are indistinguishable, then it immediately follows that the two electron wave function should satisfy this relation. What is that relation? It is, what is this relation? This is, let's say this is the probability of finding two electrons, 1, 2, in the volume element dq1, dq2. Okay, that should be equal to the probability of finding two electrons with the reversed, because they are indistinguishable, right? So then this relation should be satisfied, and once this is satisfied, this immediately follows that psi 1, 2 can be either plus psi 2, 1 or minus psi 2, 1. Okay? Is this clear? Because here this probability of finding either two electrons 1, 2 or 2, 1, because they are indistinguishable in a given volume element dq1, dq2, that probability should be conserved. That should remain the same. Okay? Once you say that, then psi 1, 2 is either plus this or minus this. Okay? Plus minus this. Psi 1, 2 should be plus minus psi 2, 1. Right? So this solution is called the symmetric, because this is, wave function is symmetric under the interchange of electrons 1 and 2. Okay? Whereas here there is a change in the sign. That means that is a wave function which is antisymmetric with respect to the interchange between the two electrons 1 and 2. So if you take the one electron functions, product functions which we had taken earlier, when we considered them to be non-interacting to electrons and distinguishable, then those, if you use those product wave functions, then none of them actually satisfy these conditions. Okay? None of those functions, which was this, let's go back, none of these functions, whether this or this, satisfies the symmetric wave function or antisymmetric total wave function of the two electrons. This fellow has spin down. Okay? So it corresponds to spin up, spin down, then minus spin up, spin down. So what does it mean? It means that the total spin should be equal to, in this case the total spin is 0, obviously. Up, down, up, down. Okay? So it is 0. This corresponds to a spin singlet. This corresponds to a spin singlet. So that is the only possibility there, because we want this spin part of the wave function to be antisymmetric. So this is the only combination that will give you that. Okay? Right? Here you have interchanged these particles. Here, the electrons have been interchanged with respect to this. And that gives rise to this negative sign. Right? Now, in this case, where the special part is antisymmetric polarity, the spin part has to be symmetric. Now, in that symmetric case, what can happen? Either both the electrons have spins up, or both the electrons have spin down, or they have one up, one down, but with a positive sign in between. Right? So that means you should be spin up, spin down, plus spin up, spin down. But up-down spins are now interchanged. That is the only thing that is happening between this and this. That is here electron 1 has spin up, electron 2 is spin down, here electron 2 is spin up, and electron 1 has spin down. Okay? But then there is a positive sign. So here now what does it correspond to? These are both the electrons 1 and 2 have spin up, both the electrons have spin down, and two electrons have this spin up, down, right? So now this will correspond to what? If I have to now write it in terms of ms, this is obviously a triplet state, because S1 half plus half, it's S1 state, so a triplet state. So that's why you have triplet, there are 3 different states corresponding to this. So one would be just S equal to ms equal to plus 1, ms equal to minus 1, and this will correspond to ms equal to 0. Right? So this corresponds to a spin singlet state, this corresponds to a spin triplet state. Is that clear? If it is not clear, I will repeat it. I want all of you to be with me. Because this is simple, some of you have already done. For others who haven't done it or who are seeing it for the first time, then there will be obviously some questions, some doubts. Yeah. Right. Right. So it means what? It means that this special part of the wave function is symmetric under interchange. Nothing happens. If I change 1 to 2 and 2 to 1, nothing happens there. Sign remains the same. Whereas whenever you have a minus sign in between, it's clear that that will be antisymmetric. That will change sign. Right? Okay. Now what we do is that so far we just simply said that, okay, you have two electrons which are not interacting with each other. Even though you went all the way down up to this stage where you found out that the total wave function has to be antisymmetric, because we removed only one assumption. That was, first we treated the electrons as distinguishable. Then later on we treated them as indistinguishable. But we still did not consider any interaction between them. We are dealing with a two electron system, but only thing we said is that these two particles are indistinguishable. We cannot say this is 1 and 2. Okay, it could as well be 2, 1. Right? And in that case, what would happen to the total wave function? That's all that we have done so far. Okay? Now what we do is, we have two electrons. Let us take the example of a hydrogen molecule. So we have two electrons and two nuclei. One hydrogen atom, one electron and one nucleus. Similarly here, one electron, one nucleus. Now these two hydrogen atoms are forming a molecule, right? Now what will happen? What are the interactions present? So you have electron, electron, nucleus, nucleus, and electron of one, nucleus of the other, right? So here now A, B, earlier I have used them as states, A and B. Now I am using A and B as nuclei. Okay? A and B I am using as the position of the nuclei. So this would mean this term is basically the Coulomb term, okay, between the two nuclei. Okay? RAB is the distance between the two nuclei, A and B. R12 is the distance between the two electrons. Okay? And so these two terms are positive. And then I have the Coulomb interaction between the electron on one atom with the nucleus of the other, and the reverse one, the electron on the atom 2 with the nucleus of atom 1. Okay? So that is this term. So now I have competing terms. These two are positive and they are negative. Okay? Okay, now because of these interactions, there is going to be an additional energy. It is not just simply, total energy is not now simply EA plus EB. There is an additional contribution coming from these interactions, which are basically all Coulomb interactions. Right? So now if I try to calculate the expectation value, because that is what gives you the eigenvalues E energy. So that for this Hamiltonian is given by this. So you will have, this is the symmetric part of the, this corresponds to the first one there, where the special part of the wave function is symmetric and spin part is antisymmetric. And the other one would correspond to, this will correspond to another one where the special part is antisymmetric and spin part is symmetric. Okay. So now we have to deal with this, where this A star and A, these are the coefficients which finally yield the normalization factors. They are maximum somewhere midway between A and B, where then that term E square by RAB, okay, that RAB now would decide everything else. It will finally decide whether the total J12 is positive or negative. So now you see that, so this, the two terms, that is RAB, which contains RAB at the denominator, and R12. R12 we showed that it has to be minimized, okay, by the fact that the wave functions are peaked around midway between the two nuclei. Okay. But then, if the distance between the nuclei is too much, so it depends upon how close or how far are the nuclei with respect to each other, right? So how R12 compares with the RAB also makes a difference here. So J, what will be the value of J would be decided by RAB, the distance between the nuclei. That means your so-called lattice parameter, if you want to see it that way. But in this case, it is just the distance between the two nuclei, because that are two atoms. They are placed somewhere. So then you have this exchange, integral J, which I call it 1, 2, but here JEX, as a function of RAB, has this form. Okay? That means when RAB are far apart, then only you expect the wave function to peak somewhere in midway, right? So then only it is possible to have J exchange positive. But if RAB is very small, then it will have, you will have JEX as negative. You will change sign. Okay. Now, this probably you know, you have seen this. This is called Bethes lateral curve, right? Called Bethes lateral curve. It tells you that there is a critical distance between the spins, okay, at which the effective exchange between those spins is zero. They don't experience anything. But above that critical distance, the spins would be parallel, and below that they will be antiparallel. So that means all those, like your 3D things like iron, cobalt, nickel, and 4F like gadolinium, they always have these distances in it. That means lattice spacing is such that it's above this. So they are all ferromagnetic. Whereas manganese and chromium, they lie in this region. Their interatomic spacing is smaller, and they lie in this region. But then, if you alloy manganese, or you go for Heisler alloys, then obviously the distance, manganese distance increases, so that finally, or you have like manganese arsenide or antimony. If you are dealing with this, manganese arsenide, manganese antimony, they are ferromagnets both, and with lattice spacing which is 2.8589. Whereas if you take pure manganese, the spacing is 2.58 angstroms, which lies below the critical distance. Okay? Okay. So far what we saw is the energies that we computed E1 and E2, that was based on only the spatial part of the wave functions. The spin part didn't appear there at all. Okay? But then we want that to find out how the energies of these electrons depends upon the spin orientation of the electrons. Okay? So now, how will the spin things suddenly appear when they are absent already in the calculation of E1, E2? Okay? How does it appear? Or when we say that the spin degrees of freedom commute with the spatial degrees of freedom, then if I am dealing with only the spatial part, why should you bother about the spin part? You understand what I am saying? So why is it important for you to know how the energies would depend upon the relative orientations of the spins at 2 electrons? Any idea? Why is it important? Because what you saw is this is dictated by the indistinguishability of particles, or the antisymmetric total wave function has to be antisymmetric. We saw E1 was corresponding to that wave function for which the spatial part was symmetric and spin part was antisymmetric. So, in a way, what is happening is that if the spatial part of the wave function is symmetric, then it forces the spin part to be antisymmetric, and vice versa. So even though there is no direct relation between the two, but there is an indirect relation. That means because the total wave function has to be antisymmetric, that condition has to be satisfied. So the symmetric spatial part of the wave function forces the spin part of the wave function to be antisymmetric, and vice versa. That is where this spin thing comes, because it depends upon now the spatial configuration. Okay, whatever be the spatial configuration, that will decide what sort of a spin configuration you have. Right? So that has to be brought out very explicitly. It is there, but just because the spin, the H12 did not operate on the spin part of the wave function does not mean that the spin part of the wave function is absent. Right? It is there. It is because the Coulomb interaction that operators do not operate on the spin. Okay, now what we do is that the simplest way to know what is the relative orientation of the spins of the 2 electrons would be a dot product between the 2 spins, S1 and S2. Because then I know the projection, if I keep one vector, one spin to be some quantized direction, then I take the projection of another vector on this. So that will be invariably a dot product. Right? And now I am dealing with 2's, right? L cannot respond because it's already locked in the electric field direction. So that means that I will have only spin-only value, because only the spins are responding to the magnetic field. But if the spin-orbit interaction is really strong, then, and if the Zeeman interaction is such that it can overcome that, then it is possible that once the spins are getting oriented, then because of the strong spin-orbit coupling, even the orbit tries to reorient itself. So then the contribution will come from both spin as well as orbital angular moment. Is this clear? How much time do I have? Okay, because exchange, as you have seen, would depend critically on the distance between the spins. Exchange, okay, one more thing before I go there. It's important for you to understand this. Now, when we say exchange interaction, what do we understand by that? What is, if someone asks you, what is exchange interaction? How will you explain? From this it was clear what the exchange interaction is. That was the title of this lecture, exchange interaction. So if someone asks you what is exchange interaction, what will you say? How will you respond? No. Sometimes it's called quantum mechanical quantum mechanical exchange interaction. So how is it, I mean, how do you explain to someone who asks you this question? What did you see? What is J12? J12 or J, whatever. What is that? What sort of an interaction is it? J1J is what? J12? Yes. Basically the Coulomb interaction. As you have seen, the difference between K12 and J12 was K12 was there was no interchange of particles, right? But there are Coulomb interactions. Same thing in J12, except that the particles were interchanged. So that is the Coulomb interaction when the particles are interchanged, but the Coulomb interaction. So exchange interaction is basically Coulomb interaction, but this Coulomb interaction is modulated by a spin-dependent interaction which is coming through the Pauli exclusion principle. Understand? That means if the two, for example, what it means is the following. If for the time being we ignore the spin on the electrons, then there is a Coulomb repulsion between the electrons, okay? And the Coulomb interaction would see to it that there is some distance that these electrons have to be apart, okay? They have to be some distance apart. Now, depending upon the spin orientation, suppose the electron 1 has spin up and electron 2 has spin down. Now, according to the Pauli exclusion principle, what should happen? The total system will lower its energy if this spin comes closer, right? So that means now there is again some distance, which is, so there is a Coulomb cost that you are paying by bringing this spin closer, but the reduction in the energy because of the Pauli exclusion principle, that energy reduction is much more than the Coulomb cost that you are paying. So the spins are coming, antiparallel spins are coming closer together, okay, than what the Coulomb interaction would have dictated. Is this clear? But suppose now the two spins are parallel, then this spin will try to avoid this spin even further. So from the Coulomb part, whatever, if this was the distance which was determined by the Coulomb interactions, then the two electrons which have spin. So basically now this del square u dot u would be given by this, and then you use, this is the, if there are any questions, because I am sure that some of you have already done that, and may not be in magnetism, but definitely in quantum mechanics would have done that 2 electron problem. Okay, but then it was important to get this in the proper context so that one understands what is the basis. So as it turned out that when Heisenberg gave this derivation, then it was immediately realized that quantum mechanical exchange is at the root of the molecular field that we are talking about, the Weiss was talking about earlier. That was much before the advent of quantum mechanics, okay, which he postulated. And the understanding was simple, but at that stage, at that time, it was profound. Because the understanding was the following, that since for a ferromagnet, you know that when you plot M versus H, for a ferromagnet, the M versus H, it starts very fast if you are applying field, of course, in the easy direction, and it saturates very fast. Now, compare this with the case when finally, of course, this will also get saturated at the same value. Compare it with this. What is this? It's linear over a large range. This is a paramagnetic sample, right? Paramagnetic sample, it will mean that this slope is going to be small because each individual spin is moving in the direction of the field.
independent of the remaining spins in the system, right? Because they are non-interacting. Okay? Now, based on this, how will you explain the sudden increase in the magnetization at very low fields and then saturating eventually? How do you explain this? But nonlinear, yes, you can see it is nonlinear, but what do you infer? There has to be interaction, yes. Linear means that there is superposition principle holds. So then it's just the sum of the individual moments in their components on the field direction and so on. That is fine. But why should this just simply increase so fast? That means instead of individual spins going in the direction of the field, suddenly group of spins is just responding and going in the field direction. That's why there is a sudden increase in this. So he had to postulate domains, even though nobody had seen domains at that time. Okay, so he had to postulate domains, and he said that within these domains there is some internal field, some molecular field, which is keeping this in the same direction, so that this whole spin patch just suddenly goes into the field direction, and there is a very large jump in magnetization that occurs even by the application of a small field. That's how Wyeth thought in those terms at that time, and thought that there has to be